So good afternoon, everybody. You can ask your questions, or maybe I can take some questions from the list. These questions are not coming with names of the people who have asked them. Which person has asked all those questions? And their things also come here, no? Whatever they write or something. It will not come there. On that other screen, it could have been linked so that I can see it, but I can't. I don't know able to see here. Who is saying what? Then is better. Hmm. Rather than me seeing myself, let me see what they are writing. Let them see me. All in. Please, otherwise, how the interaction will happen? Mm-hmm. You may have to read it for me then. Mhm. But why to answer if nobody is there to listen? Mhm. Okay, this is for live interaction. So the person should be around. The recording of question answers. If nobody is around, for all you know. Mhm. See, watching now. When they are quiet, those three who are watching can ask something. ऐसे भी कोई कुछ पूछ नहीं रहा है, सब शांत। हाँ, तो इसलिए क्वेश्चन है उसको We should start discussing our Poisson ratio problem, right?
That's a post regarding
You can buy that with Poisson never. और इसको कुछ पूछे बात करें और लाइव सेशन is only instructor is live. That number is also not changing. It's neither increasing or decreasing. That is also some sort of frozen number, right? That's the live chat. So that is from our side. No? Yes, Arnab Sarkar. Hello, sir. I have one question. What is the relationship between ductility and hardness of material? Thank you, Arnab. Thank you for asking. That's a good question and that's a difficult question. And the relationship is not immediately obvious. So, as we have seen, can I write? So as we have seen, if we have a stress strain diagram, then we have an yield stress sigma y and a strain to fracture EF. Ductility relates to the strain to fracture. So this is a measure of ductility. Whereas sigma y is the strength parameter, and this will relate to hardness. Not exactly hardness because this is a tensile test, but in general, the higher hardness material will also have higher yield stress. So hardness is a y-axis parameter, a stress parameter, whereas ductility is a strain parameter. Now, in principle, the two can be independent. So you can have, if I can draw another, if I can change the pen color, yeah. So this is the highlighter. So I can have very high hardness but less ductility, or I can have low hardness and large ductility. All these are possible, and usually for metals this is the relation which we have, that if somehow if you increase the ductility, the hardness comes down. If you increase the hardness, the ductility comes down. However, there are some processes, for example, something called severe plastic deformation. Severe plastic PD. In some of these processes, it has been shown that you can increase both hardness and ductility. The relationship between the two is not obvious, and I cannot give a simple formula for the relationship between the two. The two, in a sense, are independent property of the material, but they are interlinked also. I have just Pradyut Nath. Hello, Pradyut. Difference between hardness, strength, and toughness. Hardness, strength, and toughness. So we were just discussing the difference between hardness and ductility. Hardness and strength, the two are interlinked one thing. So strength usually we take in a tensile test. If you are talking of tensile strength, then yield strength or the ultimate tensile strength. These are the two parameters which are used as a strength. Strength parameter. The yield strength is resistance to plastic deformation. It's a measure of resistance to plastic deformation. Hardness is another measure of resistance to plastic deformation by indentation, where you indent an indenter into the material. The stress field in the two are different. Here, of course, there is a very simple stress field, and that is uniaxial stress. Uniaxial tensile stress. Here, oh, I have changed the page. Can I go back? How to go back? Did I just push it? So this is hardness. In hardness, it's a more complex stress field. because when indenter will push in, there will be all sorts of compressive, tensile, shear field generated in the region which is deforming. However, the two are interlinked because both are measuring the resistance to plastic deformation. So if you have higher hardness, you also expect to have higher yield strength. Toughness again is toughness is used in various sense. So one in one sense, toughness is the tensile toughness. In tensile toughness, toughness is just the area under the stress strain. Sorry, area under the stress strain curve. So this area, this is toughness. But another measure of toughness is the so-called impact toughness, which comes in Charpy test. Which measures toughness in high rate of deformation. So there, of course, you break a sample. You have a rectangular sample with a notch, and you hit it with a hammer and break it. So how much energy is absorbed in fracture? This is also in a sense energy absorbed in fracture. In tensile test also you have energy absorbed in fracture, but it is done in a slow test. The strain rates are very low. In an impact toughness, it's energy absorbed in fracture, but the rate of deformation is very high. Can I bring it back? Sorry about that. I'm trying to get back the page on which I was writing. Yes, and how to go to the new page, but I have exhausted this page. Can I go to the next page? Yeah. There is of course a third kind. These two we have mentioned in the course. There is a third kind of toughness test also, and that is called the fracture toughness. We have not really discussed this in this course, but that is so fracture toughness is related to our Griffith's formula, 2e gamma by pi a half. So if you write it as sigma f square root of pi a, then you find that it is 2e gamma by half. You can, so this is a material property, and you can define this material property as some sort of fracture toughness. So that is called Kc. This is stress intensity factor, critical stress intensity factor. This is also a measure of toughness. So I have given you three different senses in which toughness is used in material science. One is this fracture toughness, coming as sigma f square root pi a at the point of fracture. This is called fracture toughness. Then you have tensile toughness, and then you have impact toughness. I hope I have given you some idea of the 3 points. Uh, in between there is Guru Murthy. Can you explain the difference between sessile and glissile dislocation types? Yes, this is a simple definition. Uh, mm, so can I go to the next page again? How to control that myself? This arrow gets you to the new page. Yeah. So sessile and glissile. Sessile means stuck, not moving, and glissile means able to glide. Not able to glide. Able to glide. So a dislocation which is lying in a nice slip plane. Suppose there is a in consider FCC, consider cubic flow pack. In cubic flow pack, we know that the slip planes are the 111 type of plane. So if a dislocation is lying on this plane and is of the right Burgess vector, and the Burgess vector is supposed to be half 110 type. If a dislocation is lying on this plane and having this Burgess vector, it can glide. So it will be it can glide. So this is able to glide. Shrikant sitting here is correcting me that it should be bar 100 to make him happy. Let me put this bar 110 to satisfy Weis's law with the plane written here. But since this is a grouped thing, we are always knowing that we can select suitable one. So this will be glissile. But suppose a dislocation line with the same Burgess vector is now lying on a different plane, 100 plane. If the dislocation lies, so that dislocation will become sessile, because 100 plane is not a favorable slip plane. In other words, the stress required, the critical resolved shear stress required to move the dislocation on 100 plane is very high. So if it lies on 100 plane, then it will be a sessile dislocation. Pradyutnath is now trying to find a relationship between resilience and fracture toughness. No, the two are independent properties. One is relating the energy absorbed up to elastic limit. So that is important in design of springs, for example, because you want to regain the energy back. And the other is toughness, which is up to the point of fracture. Kindly explain screw dislocation Burgess vector. Can you little bit explain your question? Means screw dislocation, of course, I can define screw dislocation. Okay. I can define screw dislocation as a dislocation line whose line vector, of course, will be parallel to the dislocation line. But if the Burgess vector also is parallel to the dislocation line, it's screw dislocation. That's our definition. But what exactly you want to understand about that? If you explain your um, question a little bit more, I can try to address. Why there is no n-centered tetragonal lattice in the Dravelis? That I have explained in my, I think so, my lecture. So you have any difficulty in the way I have explained in the lecture? How does Arnab, how does stacking fault and twin boundary affect properties of material? That's a difficult question. Yes, both boundaries will also act as obstacle to dislocation motion. So both boundaries will of course enhance the strength by their very presence. If you have more stacking fault and more twin boundary, the material will be stronger. So the mechanical properties is affected. Twinning, yeah, deformation. Yeah. Twin and stacking fault both can form during deformation. I think so. Live questions I have answered. I don't know that why there is no end-centered tetragonal lattice. So you have any difficult, Pradyut? I am asking you, Pradyut Nath. You have asked why there is no end-centered tetragonal lattice in Brevelis. I think I have discussed this in my course. If you have any further difficulty, you please try to explain. And I'm also waiting for the clarification on the question on screw dislocation. That what exactly you have said, kindly explain screw dislocation, Burgess factor. Exactly what you want. But you are already thanking me. Okay, sir, thank you. But I have not answered your question. I am asking for clarification on your question. Is there any other factor responsible for ductility rather than slip system? Yes, slip system is one of the things, and it will not explain the ductility completely because yes, all generally we use slip system to distinguish between HCP and let us say FCC. That FCC has 12 slip system, whereas HCP has only 3 slip systems. So we say that FCC is more ductile than HCP. But then all FCC materials do not have the same ductility. Some are more ductile than others. Gold is definitely much more ductile, it is FCC, than nickel, which is also FCC. So ductility will not depend only on slip system. There are other factors, but what? So definitely there are other factors, but what those factors are is a difficult question, and I cannot pinpoint. Particularly ductility is, I think, the most difficult property to to understand in terms of micromechanism. For example, in our course also, if you see, and in most courses in material science, a lot of theory and a lot of development is done for the strength, the yield strength. So for yield strength, we have the dislocation-based theory, but for ductility, we don't have any such dislocation-based theory or something. So ductility is usually the measured quantity, and we accept what we are having. But to explain ductility, in terms of more fundamental things like dislocation, at least I'm not aware of. How does a screw dislocation occur? Pradeep Nath's question. One of the ways in which the screw dislocation occur is during the crystal growth. So during crystal growth, if uh, if a dislocation nucleates, a screw dislocation nucleates, it provides an easy surface because on the surface there will be a step, and on that step the growth will happen. Whereas otherwise, if the screw dislocation is not there, you will have a flat surface, and there will be each time that flat surface grows, the new you have to have a new nucleation onto that flat surface for further growth. So nucleation becomes more difficult in a crystal without a screw dislocation. No, I have already accepted my ignorance regarding the factors responsible for ductility. So we know, for example, that most of the strengthening mechanisms reduce ductility. So you can say alloying increases strength, so alloying decreases ductility. Similarly, strain hardening increases strength, in strain hardening decreases ductility. So you can, if you want to think of these as factors responsible for ductility, you can think of them like that. So a higher dislocation density produced in strain hardening leads to reduction in ductility of material, if that is one of the factors you would like to consider. Do you have any other answer to that? Okay. Ductility factors responsible for ductility. Yeah. Presence of crack can also control ductility. Presence of large cracks will reduce ductility, but crack will grow and you will not get much plastic deformation. Somebody asked that, so let me show that, so that that's my favorite question anyway. That why end-centered tetragonal is not there. Yeah, please share it. Share it. So let me try to answer why is end-centered tetragonal not there. In fact, it is an interesting question and it has two answers. The answer depends upon how you are end-centering, because there are two ways of end-centering. You can end-center. So this is a simple tetragonal at the moment. This is a simple tetragonal. Lattice points only at the corners. If I want to make it end-centered, I put lattice points also at a pair of opposite face. But the pair which I choose can be in two different ways. I can choose them I can choose them on the, how come it got slipped? So I can choose them on square faces, top and bottom square faces, or I can put them on the left and right rectangular faces. And these two cases have different answers. And the answer is based on symmetry. So when you put on square faces, you have not disturbed the fourfold symmetry of the tetragonal lattice. So it has the fourfold symmetry. So it remains tetragonal. But then why it's not listed in the Bravais list? The reason for that is that if you now consider the crystal, sorry, you consider the lattice with other unit cells. So I am now putting one more unit cell. Then you can see that in this, you can, maybe I should use red. You can now select a new unit cell, which is a primitive tetragonal. So by centering, the fourfold symmetry was not lost, so it was tetragonal. But a smaller tetragonal unit cell, primitive tetragonal, is possible. So I will say n-centered tetragonal is not there because it is primitive tetragonal. But this case is even more interesting. Here you see that as soon as I put on the rectangular faces, this fourfold is lost. This is no more a fourfold because now I cannot rotate by 90° about it. I have to rotate by 180° to get from this to this because front and back faces are not centered. So the fourfold symmetry is lost and this becomes twofold. As soon as the fourfold is lost and only twofold remains, this is no more tetragonal. So it goes into orthorhombic. Of course, orthorhombic requires not one twofold but three twofolds, but those three twofolds are there. This is also twofold and this is also twofold. So you have a twofold here and you have a twofold here. So you have three mutually orthogonal twofolds. So it's an orthorhombic. And in orthorhombic, you have this n-centered orthorhombic. So this turns out to be n-centered orthorhombic. So this case of n-centered tetragonal is not there because it will degenerate into primitive tetragonal. This case of n-centered tetragonal is not there because this will become n-centered orthorhombic. Interesting case here is that although I am calling it n-centered orthorhombic, but if you see the shape of the unit cell, it is A and B equal to A and is not equal to C. The unit cell shape is tetragonal, but still symmetry is orthorhombic, and this shows the priority of the symmetry, and we will call it n-centered orthorhombic despite the equality of A and B axis. So tetragonal like unit cell is there, but lattice is still n-centered orthorhombic. This kind of equality is called accidental equality. So I have an orthorhombic unit cell in which A and B are accidentally equal. Now there is this interesting question from Guru Murthy. Example for calculating nucleation rate and growth rate. Assume some numbers and show me. Sorry, Guru Murthy, I'm not uh, ready to do a calculation right away here. I need more preparation for that question. to answer that question. You have given a question to calculate nucleation rate? I don't think I have given it in my lecture. Yeah, yeah. But that's just a definition. Means nucleation rate is the number of nuclei forming per unit volume per unit time. So of course, if volume is given and number of nuclei forming in a given time is there, then you can simply divide number of nuclei by the volume and by the time. So you will get number of nuclei forming per unit volume per unit time. So that is one way of calculating, but that is the definition. I thought that when you are asking for calculation, you are you are asking something deeper. That how to calculate nucleation rate in a certain given system. Let us say copper undercooled by this much temperature. What is the nucleation rate? That question requires a little bit more attention. But by definition, of course, we can define and calculate. And growth rate is just the velocity of the interface. At what rate? So, for example, yeah. So, if that is what you are asking, then it is a simple question and I can answer. That I have a volume, let us say volume V, and I spend time T, and in time T I see 1, 2, 3, 4 N nuclei forming. So since N nuclei form in volume V in time T, so N by Vt will be the nucleation rate I. Will, will be the units will be per meter cube per second. Per meter cube from V and per second from T. And growth rate is when a particle is there and it's growing. So suppose radius increase in dr in time dt, then the growth rate g is simply dr by dt. So that is meters per second. Arnab has a new question. What are phases present in hypoeutectoid and hypereutectoid steel? Can you explain the formation of such phases? Yes, I have already done that in my lectures, but if you want me to do it again here, I'm happy to take that question. See, let us look at the iron carbon diagram. Let's look at the iron carbon diagram. So you have 0.02, 0.8, 8% carbon. You have temperature, this is 910, and this is 725, the eutectoid temperature. You have gamma, alpha, alpha plus gamma, gamma plus Fe3C, and alpha plus Fe3. Steels with less than 0.8% is hypoeutectoid. So these steels are hypoeutectoid. And steels with higher than 0.8 are hypereutectoid. Both these steels, so whether I am in a hypoeutectoid, so this will be a hypoeutectoid steel. This will be an example of hypoeutectoid. and this will be an example of hypereutectoid. But you can see that at room temperature, whether you are hypoeutectoid or hypereutectoid, the phases present is only alpha plus Fe3C. So the phases present in both the alloys will be alpha plus Fe3C. Only their amount, their ratios will be different. You can see in hypoeutectoid, it is closer to the alpha side. So hypoeutectoid will have more alpha, less Fe3C, compared to hypereutectoid, which is away from alpha. So it will have lesser alpha and more Fe3C. So both alloys will have alpha plus Fe3C. Only how alpha and Fe3C form will be different. So you can see by the cooling. That you can see by the cooling. So if you cool this alloy, as it is cooling, it is first forming, it is going into alpha plus gamma, so alpha will form, alpha forms, and then remaining gamma forms into alpha plus Fe3C. So the way it forms alpha plus Fe3C is first only alpha, and then alpha plus Fe3C, which is the perlite. But in the end, it is only alpha and Fe3C. Alpha is occurring in two ways, inside perlite as well as outside perlite. But when you cool this one, you can see that it first goes into gamma plus Fe3C. So Fe3C forms. So the way it will form alpha plus Fe3C, that it will form Fe3C plus alpha plus Fe. So that is perlite. And Fe3C here we call pro I will call it proeutectoid cementite, and here I'll call this proeutectoid alpha. I hope I have answered your question. Arnab, you are okay with this answer, or you want something more? Hmm? Sorry? Yeah. No, 5 minutes is there. If there are no more questions, we can thank Guru Murthy, Arnab, and Pradyut Nath. Those were the people. The question left. Difference between crystal system and Bravais lattice. Writing complete derivations and few concepts is mandatory, or is it okay to write only equations? We ask only objective questions. This question is not relevant to us. If you are asking for some other exam, that depends upon the examiner and their system. Which book is best to prefer? We have used Raghavan as our textbook. That is mentioned in the course somewhere. In the introduction, course introduction, we have said that we are using Professor Raghavan's Introduction to Material Science and Engineering as our book. What is the difference between crystal system and Bravais lattice? We explained I took a lot of pain in explaining this at the beginning of the course, that we have two kinds of symmetry, the point group symmetry and the space group symmetry. Point group symmetry, only rotation, reflection kind of symmetry, except translation. So all symmetry except translation is point group symmetry, which leaves one point unchanged, at least one point unchanged. When you classify on the basis of this symmetry, you call it a crystal system. So there are 7 kinds of such symmetry grouping, and they give you 7 crystal systems. When you classify a lattice on the basis of a space group, which includes translations, you have 14 different space groups. These are called 14 different Bravais lattices. So I can give you an example if you can show me. So let us look at the cubic system. In cubic system, we know that there are 3 cubic lattices: simple cubic, face-centered cubic, and body-centered cubic. Simple cubic, body-centered cubic. So simple cubic, the lattice points are only at the corners. Body-centered cubic, lattice points are at corners as well as body center. And the face-centered cubic, lattice points are at corners as well as centers of all the faces, left and right, top and bottom, and front and back face center. Now, if you look at it from the rotational symmetry point of view, if I am focusing on the rotational symmetry, all of them have, whatever is the centering, all of them have along the body diagonal a threefold axis. And there are 4 body diagonals, so there are 4 threefold axes is there. So irrespective of the fact that one has point in the center, one has points at the face centers as well, that does not change, does not affect their rotational symmetry. All of them have the same rotational symmetry, and the characteristic rotational symmetry, as we said, is the threefold along the 4 body diagonals. So along all the 4 body diagonals, each of those body diagonals, you have threefold symmetry, and this is true for this, as well as this. So since they have the same rotational symmetry, we classify them into same crystal system. Same rotational symmetry, that is same crystal system, and in this case, that is the cubic system. So we have cubic crystal system based on the rotational symmetry. However, if you now look at the translational symmetry, you can see that in the case of simple cubic, there is no translation in available from corner to the center of the face, because in the center of the face there is no lattice point. Whereas in FCC, there is a translation from corner to the center of the face. So in terms of translation, simple is different from face center. So they belong to different space groups. Similarly, there is no translation from center to the corner, center to the body center in case of simple, whereas there is a translation from simple to body center in the body center. So again, they are of different space groups. So in terms of translations, all these three are different symmetries. They have different symmetries. So when you look from the translational point of view, you classify them as different space groups. So we have three different Bravais lattices, in cubic system. The cubic system, same rotational symmetry, but three Bravais lattices, three different translational symmetry. What fraction of projectoid alpha present in a hypoeutectoid steel at above or below eutectic points? There will be no projectoid alpha you use above the eutectic or eutectoid. You mean eutectoid, and now you have used the wrong phrase. You are meaning to say eutectoid point. So above the eutectoid point, you have alpha, but that is not labeled as proeutectoid alpha. That is just alpha because it is appearing with austenite. Below the eutectoid temperature, the austenite changes into alpha plus Fe3 per line. So below the eutectoid temperature, alpha appears in two forms. One, the alpha which formed above the eutectoid temperature, and another alpha which formed at the eutectoid temperature as a pylitic reaction. These two alpha you want to distinguish below the eutectoid temperature. So below the eutectoid temperature, alpha which had formed above the eutectoid temperature, you call that hypoeutectoid alpha, and alpha which has formed at the eutectoid temperature as a part of Perlite reaction, you call that eutectoid alpha. You can look at my video again, and I think I have explained that. And the fractions can be found simply by drawing the tie line. Maybe I can try to show. So let me try to show what I was telling. So let me take a hypoeutectoid steel. This is gamma. This is gamma plus alpha, and this is alpha plus B3C. If you look at the microstructure here, it is austenite. So you have grains and grain boundaries of gamma. All are gamma. If you look at the microstructure here, you have now you gamma was already there to begin with, but now you have come into the gamma plus alpha regime, so alpha will form. So there are some alpha regions. Let us say these are the alpha regions which are formed. Showing them forming on the gamma grain boundary because heterogeneous nucleation is more favorable. But some of them may form homogeneously inside also. So this is the situation there. Then if you cool further, and come here, then whatever the remaining so let me again create red. So let me create, maybe not red. So let me create. So whatever alpha which had formed beforehand will remain, but now new alpha will start forming as part of the pearlitic reaction. So since I have used alpha red for alpha, let me use red plates even in pearlite. So red plates of pearlite are alpha, white plates are cementite. So whatever I am leaving as white, you can assume that that is cementite. So alpha, 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 and in between cementite. So this is what we are calling pearlite. This is pearlite, which is alpha plus Fe3s. And this is alpha, which formed before the eutectoid reaction. Eutectoid reaction took place at this horizontal. This alpha was had already formed before that reaction. So we call them pro-eutectoid alpha. To find the fraction, since this alpha pro-eutectoid alpha formed above the horizontal, to find it, you have to draw a tie line which is in the gamma plus alpha region, just above the eutectoid horizontal. Because you can see alpha was forming, pro-eutectoid alpha historically was forming, although you are observing it at the room temperature, but in terms of history, it formed in the gamma plus alpha region. If you want to find its fraction, you should draw the tie line there and find the fraction of alpha, which will be this arm divided by the total arm. The fraction of alpha which you get above the eutectoid temperature, just above the eutectoid temperature, will be the fraction of pro-eutectoid alpha just below the room eutectoid temperature. Or since this curve is almost vertical, that fraction will not change much as you cool. So that is the fraction of alpha, pro-eutectoid alpha, which you will have at the room temperature. So I think time is up, and thank you very much. Thank you for interacting. Initial start was slow, so I was even wondering that if anyone is around and whether we will have any interaction. But now I think we have had some fruitful interaction. Thanks a lot.